All right, folks, let's go ahead and get started. I do want to welcome you back to Unit 16. This is Reaction Kinetics. If you're following me in the Zoomdoll book, this is going to be 12.6, a model for chemical kinetics. And I think I'm going to be able to fit in 12.7, which is Catalysis, on this one as well. So let's see how we do on time. So let's start with this idea that concentration is important in determining reaction rates. But we started out the unit saying that concentration was only one of a couple of things that affects reaction rates, and temperature was another one. So how do we fit these things into a common theme? Well, and by the way, with regard to temperature, it's not a minor component of what increases the reaction rate. If you increase reaction rate, the temperature, the rate constant goes up exponentially. So it doesn't just go up, it goes up a lot, right? In fact, for every 10-degree rise in temperature, for every 10 degrees increase in temperature, the rate constant and thus the rate doubles. That's just a kind of a rule of thumb, but it's nice to keep that rule in mind. So the collision model states that molecules must collide to react. So the collision model is the model that we're going to use to explain how temperature and also concentration play into this idea of reaction rates, right? So in order for reactions to happen, the molecules themselves have to come together. They have to collide. But as it turns out, only a tiny fraction, a very small fraction of collisions produce reactions. So we have to ask ourselves, why? Well, that's the exact question that an individual whose name was Arrhenius asked in about 1870. And what he came up with was the idea that there was some minimum amount of energy that the particles must collide with in order to activate what he called the activated complex. So the activation energy then is that minimum amount of energy that must be put into the reaction in order to have a successful collision. The energy of activation. So let's take a look at a potential energy profile. These we've looked at before when we were talking about exothermic reactions and endothermic reactions. And by the way, this would be an exothermic reaction because the products have a lower potential energy than do the reactants. But what we want to interest ourselves with in this unit is, first of all, where is the activated complex? Well, it's the very peak of this diagram right here. So that's the activated complex. And by the way, the reaction is H2 plus F2 yields 2HF. Let me just write that. H2 plus F2 yields 2HF, right? But in going from hydrogen gas and fluorine gas to 2 hydrogen fluorides, we have to pass an activated complex, and that's going to cost energy. That's the activation energy. So the energy from the reactants to the very peak is called the energy of activation, or the activation energy. So what Arrhenius proposed was that in order for the reaction to proceed, to go from reactants to products, you had to match or exceed the activation energy. Well, exactly is the activated complex? Well, it's kind of an intermediate. It's an unstable intermediate between the reactants and the products, an unstable intermediate that occurs at this peak right here. Once the activated complex has been formed, then it's rare that it's going to come back the other way. Once the activated complex is formed, you're generally going to get products from that procedure, okay? So the collision theory then is a theory that explains why we are going to have collisions some of the time, but not all of the time, right? Or we're going to have successful collisions, I should say, some of the time, but not all the time, because some of the collisions will not result in a high enough energy. There won't be enough potential energy to reach the activated complex. All right? Now, we know that for any given sample of reactant, for any given, say for example, it's a gas, there's a distribution of velocities, right? So some of the particles are going slow, some are going much faster, most are going some average or some median velocity. But there is a small population that is going to have a high velocity. Well, that follows then, it follows that if you have particles that have high velocities, you're going to have collisions that are also high energy collisions. Now, they won't happen all the time. In fact, they'll only be rare. But it's potential, they have the potential to produce a successful reaction. Now, let's take a look at this diagram here. We're going to graph kinetic energy versus the number of molecules, right? So, let's take a look at T1. T1 is some temperature. Let's say it's, I don't know, 80 degrees, all right? Like that, right? 80 degrees. And if we look at the area under that T1 curve, we can see that there's some concentration, but everything under the T1 curve is the population of all the kinetic energy of all the particles at T1, right? But there's this population that exists above the activation energy. Those particles have the potential to produce product, right? But what happens if we increase the temperature? Say we increase it to 90 degrees, right? What's going to happen to the number of particles that have sufficient energy? I'm going to change the color here so you can see it a little bit better. That have sufficient energy to reach the activation energy. Well, as you can see, for T2, the curve is shifted over. You have more particles. Now you have all of these particles that have the sufficient energy. So again, we're using this collision theory idea with a minimum energy called the activation energy in order to help us to explain why some collisions are successful and some are not successful. All right? Now, as we increase the temperature, we increase the number of particles moving with sufficient energy to overcome the activation energy. That's kind of a summary of that graph right there. But it's not the whole story, because as it turns out, even if you consider those particles that have sufficient energy, kinetic energy I should say, to have a successful collision, only a small fraction of those actually result in a successful collision. So what else is going on here? Well, let's take a look at this diagram here. We have A colliding with BC to form AB plus C. Now, in this particular case, in this first case, the A and the B were aligned so that when they collided, right, they were together. C was on the outside. That orientation resulted in a successful reaction, a successful collision. Of course, that's assuming that the minimum kinetic energy requirement has been met, right? But look at this second experiment right here. We have A plus CB, but the CB or BC is not oriented correctly, all right? There's sufficient kinetic energy, but there's just not the right orientation, right? So let's kind of summarize what we've got. In order to have a successful reaction, two things have to happen. You have to have sufficient energy, you have to have sufficient kinetic energy, but you also have to have the right orientation, right? You have to have the right orientation. And there's some complicated equations that help you calculate the percentage of successful collisions and so forth. We're not going to concern ourselves with those, but we are going to look at this reaction right here. We want to be able to calculate energy of activation, right? And there's an equation called the Arrhenius Equation. This equation I'm showing here is actually not the Arrhenius Equation, but it's a derivative of the equation. And generally, what happens is if you want to determine the energy of activation, that's that right there, you're going to look at a couple of different trials at different temperatures, right? Now remember the K's are temperature dependent. So we have the natural log of K2, so that's some reaction we'll call K2, over K1 is equal to the energy of activation over R, and that R that's shown there is this R right here. It's 8.314, just like that. 8.314 is that R right there, okay, times 1 over the temperature. Let me make that arrow a little better. There we go. 1 over the T1 minus 1 over T2. Now be careful with how you write these in. It's K1 over K2 on the log side, and on the temperature side, it's 1 over T1 minus 1 over T2, right? And you can, from these two data lines, right, you can calculate by multiplying or manipulating algebraically, you can calculate the energy of activation for a particular reaction. We'll do a couple of those in class, all right? So that's that. And we're going to finish up by talking a little bit about catalysis, all right? What do we mean by catalysis? Well, when we catalyze a reaction, what we're really doing is lowering the energy of activation. All right, so we've talked about the energy of activation, and by lowering the energy of activation, what we do is we provide an alternate pathway for that reaction to happen, right? And that's really all I need you to know for catalysis. There's certainly a lot more to know if you're interested in how certain catalysts work. For example, enzymes are biological catalysts. Absolutely, feel free to research that. And I'll be more than happy to talk to you about that if you'd like. But that's really all I had for you in terms of catalysis. So I told you this was going to be a short one, and so we're going to wrap this one up early. We're going to do one, maybe two more videos on kinetics, and then we will be done. All right, I'll see you in the next one. Thanks. Bye-bye.